Hi, it's Valentine from Simplistic. And in this problem, we're going to take a look at basically we have a buffer solution and we're adding small amounts of a base in the form of sodium hydroxide or acid to the buffer. And we're going to calculate what the new pH is. So to make the problem simple, the pH of the buffer is already given to us, 4.74. And we just have to kind of take it from there and just compare it from there. All right, so first of all, the first question out here is we have to calculate the new pH after adding 0.015 moles of solid sodium hydroxide to the buffer. Okay, so whenever you're adding something, we have to understand that these moles actually neutralize. So since it's the base, these moles of the base will neutralize the same number of moles of acid. So let's go ahead and write out how much moles of acid we have and then compare it with with the moles of base that was added. So moles of acid, won't write this as concentration. Let's write that as, let's call this moles of acid is equal to 0.100, and moles of base, moles, so this should be the conjugate base, which is this quantity minus the Na. So that's going to be C2H3O2 minus, which is equal to 0.100 moles. And then what we need to understand is that the base is added at this point in time, which is 0.015 moles of solid sodium hydroxide. So let's call that moles of NaOH, which is 0.015 moles. Okay, so now, given that we just mentioned that this amount of base will neutralize the acid, so let's go ahead and write that reaction. So we're going to write the added base OH minus plus the acid HC2H3O2. So the base is going to grab a proton from the acid, leaving behind the conjugate base. So that's going to be H2O plus C2H3O2 minus. All right, so we have OH minus, which, before we do this, we just say before, we write before, and then essentially before you add the OH minus, you only have this amount of acid and this amount of base. So let's write that down. So that's going to be 0.100, 0.100. Now we're going to add. So when we add the base, we added up 0.015. Now after we added, this is what will happen. All the base gets consumed. So we subtract 0.015. Since this amount of base reacts with this amount of reacts with the acid, the moles have to equal each other. So essentially the amount of acid that is consumed as a result is 0.015 as well, which is the same number of moles of base. And then because these two reacted, you formed this. So the moles that reacted of each of them, this one and this one, will give you the same number of moles of conjugate base. So out here we'll add 0.015. So when we do all that and sum it all up, we get 0.085 moles of acid and 0.115 moles of base. Now, at this point in time, we can put this into the Henderson-Hasselbalch equation to find out the pH. Now, remember, we're dealing with moles out here, and what was important to understand is because we added solid sodium hydroxide and it was a 1 liter buffer solution, we don't have to recalculate the concentration, because if it's 1 liter, then the moles over 1 liter will still give you the same answer as molar con. So let's go ahead and take these numbers and plug it in. So we get pH is equal to pKa plus log of base over acid. Okay, so pKa is already given to us in the problem, which is 4.74. Plus the log of base is 0.115 over acid is 0.085. Okay, so This term simplifies to 0.13, and if we simplify that further, we get 4.87, which is the answer. All right, so this is the pH of the solution when solid NaOH was added. Now compare it. If this is truly a buffer, then the pH should not have changed much. The initial pH is 4.74. It rose very slightly to 4.87. Makes sense. All right. For the next part of the problem, we have to calculate the pH of the solution upon addition of 10 ml of 1 molar acid to the original buffer. So for this one, to approach it the same way as before, we want to calculate what the moles is. So the moles of this would be 10.0 ml divided by 1,000 times 1.0 molar, which would give us 0.010 moles. So that's the moles of acid. All right, so to figure that out, we have to take this moles of acid, and we're going to create an equation like this. The difference, though, is to understand that this moles of acid will react with the base. Okay, so let's write that equation out. So we have acid, HCl, plus the base, so C2H3O2 minus, and that gives us HC2H3O2 plus Cl minus. Okay, so before, how much of each did we have? Before anything was added, the original solution had 0.1 and 0.1 of the acid and conjugate base. So that's going to be 0.100 and 0.100. Now we add, how much did we add? We added 0.010 moles. So that is 0.010 moles. That's the same amount of mole that reacts with acid. So we subtract that amount. So after we get that, you can add that up. And then because this amount reacted with this is the same amount that is produced out here. So we get 0.010. So that gives us 0.090 and 0.110. At this point in time, let's go ahead and plug this into the Henderson-Hasselbalch equation, just like before. So we get pH is equal to pKa plus log of base over acid. pKa is 4.74 minus, and this log of base over acid, let's plug those values in, plus log of 0.090 over 0.110, and that becomes 4.74 minus 0.087. Simplifying that, we get 4.65, which is the pH after adding acid. As again, just like we did before, if you compare this pH with the pH of the buffer, that is very close. So therefore, the buffer actually did its job. Okay, so the buffer, despite adding extra base to the buffer, the pH barely changed. Despite adding acid, the pH barely changed. I hope that made sense. Thank you for watching.